Okay, so has any tried the notebook for from TensorFlow? Wants to tell us about it, or maybe you have looked at other things in reinforcement learning that you would like to share with us? If not, I'm going to ask.
So I wanted to ask a question. Can you hear me?
Yes, I hear you well.
So I'm Pablo Martinez. So I wanted to ask a question because I think it's not clear to me yet how the agent works. So that it's been kind of confusing for me.
So you want me to explain what it does? Oh, okay. So the agent collects observations of the state, then decides on an action based on a policy, and then acts on the state to change it. That's what the agent is doing. So in the case of the game, it is the player.
Okay.
In the case of this example from TensorFlow, the agent is the part of the code that corresponds to given a state, is going to decide, let's say, in what direction is going to move, towards the left, towards the right, or with what amplitude. And this decision that the agent takes is based on this policy that is obtained.
Okay, and so the different the different agents, they just the algorithm is different to make the decision.
Yes, so sometimes the agent, when it receives the information about the state, the decision that is taken on what action is going to take on the state, that can be based on many different characteristics. For example, when in the one of reinforcement learning of TensorFlow, you are using the QLearning. QLearning is essentially creating for each of the possible moves, is creating a matrix that says, for example, let's say you have your pendulum, if you want, and on a given state of position of the pendulum, you could go to the left or to the right, and with an amplitude. And once you get to that state, the next one, you could again go to the left, to the right, with a different amplitude and so on. So a Q matrix, in the case of QLearning, a Q matrix is built in which you have all possible actions with all possible paths that you could follow to go from one state to the next. And essentially creates a huge matrix of state and possible actions. And through that matrix, you can follow a path. Maybe it's more clear in the game of Go or chess, is when we were discussing how a chess player, given the board it has in front, if he's a good chess player, is going to start thinking about, okay, if I now take this action, this will happen later, and then I could take this other action. It's creating like a tree of possibilities, of branching outs. Of I take one option, then the other guy can take the other option or that one, and it creates a huge tree. Huge trees like this can be written like high-dimensional tensors of possibilities, and this is what is called QLearning. And QLearning is, or deep QLearning, which is what you do in this notebook, is essentially building this gigantic matrix of possibilities and their consequences, and then scouting over them and using neural networks, actually finding the best path. So given a state you are in, what is the best path to achieve the highest return? And that then decides the next step. So for example, given how the pendulum is right now, you might decide that now you want to move a tiny bit to the left with that amplitude, because you know that many steps along the way, this is how you will finally achieve the equilibrium for longer and stuff like this. So this is all what the agent is doing, and is using this QLearning in this particular case. But there are agents you want that use other kinds of information, like other algorithms, like this reinforced, the DGPG, and so on. DQN is, I would say, the most intuitive one to learn. So that's why I also thought this was a good notebook. Okay, more questions or comments or anything you want to share with the rest? In case you didn't notice, but in the Slack, I have been sharing some links to papers of the use of reinforcement learning in physics, mostly reviews, so you can actually just go to them and then you will see references to other papers in that area. So that you can look at those. As I said, this is used very much in fluid dynamics, embodied dynamics, embodied physics, quantum states, time evolution of quantum states, and so on. Okay, you have more questions? I know that this notebook today teaches you how to solve a problem that you might not find so interesting. I know that also identifying digits might not be so interesting, but you know that convolutional neural networks have immediate applications in physics. So you can see how you could use this for physics. Whereas this other one is not so clear unless you are actually working on those simulations of very complex many body fluids and so on. But I thought that at least you should be able to have a notebook that you can run and you know how to call functions if you ever need to. And what is the procedure, which is always like setting up the agent, collecting trajectories, evaluating on trajectories, and then using a neural network to find the best path for each step, which is all well explained in the TensorFlow notebook. All right.
Veronica, can you hear me?
Yes, I hear you, Silvia.
I want to ask you a bit about the hyperparameters. I mean, can you describe a bit each parameter in order to understand the notebook? Because it's a bit weird for me since it's the first time that I'm looking.
Yes. So hyperparameters, the first time you hear it, you think, oh, wow, that must be like a super difficult and super awesome thing, no? With this name, hyperparameters. But you have been using hyperparameters already and fixing them when you were doing neural networks. For example, let's say on the means data set, you were deciding what learning rate you were going to use. You were deciding how many layers you were going to use, how many neurons in each layer, how many iterations you will take, or number of epochs, like batch size, and so on. All these things are called hyperparameters because they are parameters that you set at the beginning, and they set essentially how your learning is going to proceed. So it's not internal parameters that run as you are learning. It's something that you set from the beginning. And I think that's why they are called hyperparameters. So here in your notebook of today, how many iterations you are going to do, in actually how long is going to be your path until you reach this state of the pendulum pointing towards and being balanced, or the initial collect steps, or the collect steps per iterations, and all these things are essentially parameters of, at the beginning, what you need to do is to gain a sense of what your actions do on the system. Essentially, you need to understand your environment. So before you even start trying to find the best path or to learn what is the best move given a state and what is the best reward and all that stuff, you first start by scouting the environment. So that's these initial collect steps, replay buffer maximum length, and all this. And once you do that, essentially you collect a data set of things that I did and things that happened because I did them. Then you build a model, a neural network in this case, that is going to try to find and optimize the policy you are going to follow. So that given an arbitrary state, what kind of policy I'm going to take. And this is those other hyperparameters you see there, like batch size, learning rate, log interval. All these are parameters related to your modelization of the policy and of the trajectories based on a neural network. And then finally, once you learn, I mean, with reinforcement learning, you have an agent that is very good at taking decisions, then you are going to evaluate the performance of your agent. And those are these last two parameters in the hyperparameters, the number of evaluation episodes and the evaluation interval. Okay, so hyperparameters, again, is just a fancy name to say the things you are going to set, the boundaries if you want, of how often you are going to follow a trajectory, what is your learning rate for your neural network, and stuff like this. And then as is learning, many other parameters, internal parameters of your learning are changing, but not those two, those hyperparameters, sorry.
Okay, thank you.
Okay, if you have more questions or comments, we see tomorrow. We'll talk about a bunch of applications of machine learning in physics and beyond, but mostly I want to focus on applications that are directly related to physics, like the inverse problem, or by finding symmetries, also on algebraic artificial intelligence and so on. But I also want to tell you about transfer learning, because that's a concept that is used very much in applications beyond physics, but also now it's becoming also commonplace in physics. Okay, so I'll tell you about this tomorrow.